Welcome back from your break, food science. I hope you guys had an excellent long weekend. I hope that you took a little time to recharge your batteries and that you stayed safe. You ate tons of peeps if you got some of those, and that everything is going well with you. We're back and we are talking about acids and bases a little bit more today. We are going to talk about indicators and how they work and give you a little bit of practice with those this week. So here is kind of where we're going to start. This is the same slide where we ended last time we talked, and we were talking about the pH scale, and I just want to give you a little bit of a refresher to kind of jog your memory since it's probably been a little while since you've taken a look at your notes. So anyways, with your pH, remember that a pH of 7 is considered neutral. Normal water without anything added to it should have a pH right around 7. Sometimes water is a little bit lower. Acids have pHs that are lower than 7, and the more extreme you get towards the 1s and 0s of the pH scale, the more dangerous they are for you. Most foods have pHs between a 2 to a 5. Sometimes they have 6s up here like you see with potatoes, but generally foods tend to be acids. On the opposite side of things, pH 7 or higher, I should say higher than 7, indicates that you have something that's basic. Most things that are basic tend to be cleaners, and the more extreme you get, you will end up seeing them be potentially dangerous for you. So something that has a pH of a 13 or a 14 is pretty nasty, and you probably don't want to come into contact with that. Okay? What we're going to talk about today are some of the ways that you measure pH. Now, pH is something that is a calculation. It's based off of how many hydrogen positive ions are floating around inside that particular substance. Whether it's an apple or something like that, it would be measured kind of in the same way. And there are a couple of ways to do that. The easiest way and probably the most accurate way is to give you a pH meter. And that's what we were going to do in lab had we been in class. So what we're going to do is we're going to take a bunch of different foods. You're going to rip them up in the blender, basically, just totally destroy them. Filter out all the chunky parts, and then we're going to use a pH meter. And the way that a pH meter works is that you calibrate it so that it reads correctly. And then you see this kind of glass wand looking thing that's connected to the pH meter. What that does is it is technically called the pH probe. And towards the bottom here, maybe if you like poke your head really close, you can actually see that there is a little glass bulb at the bottom. And inside that glass bulb, there is some solution, and that solution is sensitive to the hydrogen ions. So it'll get a reading sent to the probe, and then the probe gives you a digital reading. So that is one way to do it. So what we would do is we're going to take the pH meter, stick the probe into it, and then record. Then we were going to compare it to our success with pH paper. Now, pH paper, I'm fairly confident you guys have used before. Oops, my bad. I'm fairly confident you've used pH paper before. It comes on little rolls and then usually has some sort of color key that you can kind of see on there. I'm going to show you how pH paper works.
Our Hydrian line of pH test papers come in a variety of ranges. We have short-range pH papers that provide colorimetric readings at fractional pH intervals, and wide-range pH papers that measure whole units across the entire scale. To use our pH papers, first check the expiration date. Then tear off a strip and dip it into the solution being tested. The paper will change color instantly. Immediately compare the color to the color chart that came with the kit. The closest matching color indicates the pH level.
Now you might say to yourself, okay, I've definitely used those before, so that's nothing crazy, but you might actually ask, how does it change color in the first place? And the way that pH paper works, and there's a bunch of different chemicals that kind of do similar things, is that they contain an indicator. So it's normal paper, and then that paper is soaked in something called an indicator. And you will either call it a pH indicator or an acid-base indicator. But what happens is they are specialized compounds that change color in solution over a very narrow range of pH values. Usually it's over 1 or 2 pH units. so that you don't have this huge range for them. And depending on the type of indicator you have, they change from just one color to another color, or they can change to a bunch of different ones. In the case of pH paper, what happens is that they are soaked in a chemical called universal indicator. And on the chart that I have below, you can see that anything that has a pH of 3 or less has kind of a reddish tint. Anything that's a pH of 4 has more of an orange tint, and then it gradually kind of transitions over the rainbow colors all the way up to things higher than a pH of 10 have a purple color. And actually, that's why, oops, this is not working. Super. Good start here. When you look at pH scales, you can see that they kind of go in rainbow order. And the reason that they go in rainbow order is because of that universal indicator color change that we talk about. So just be aware that it's not the paper itself isn't magical. The paper is soaked in a chemical that's sensitive to those changes. There are other types of indicators that you can potentially see besides universal indicator. I would say that's probably the most commonly used one, but you can see other ones. So for example, if you look here, again, this is the universal indicator color. I like this particular chart here because it shows you the color of the solution at a pH of 0 and a pH of 14 and 7, but it also shows you the color transitions as the pH changes. So you can see here it transitions all of the colors of the rainbow as we go from 0 to 14. So universal indicator is probably the most colorful one that you're going to see. There is another indicator called phenolphthalein. It is a mouthful right here. Now, phenolphthalein goes from no color to like a hot pink magenta color. And if you look here, its color change transitions much further past a pH of 7. And what you're seeing underneath the phenolphthalein here, where it says the range, that is the range where it starts to turn from no color to pink. So what would happen is if I would take something that had, let's say, a pH of 3, which would be here, and I added phenolphthalein to it, it would have no color in it. But if I would take something that had a pH of, let's say, 9, and I would add phenolphthalein in it, it would turn hot pink. Kind of maybe not even quite all the way hot pink, but a pale pink. What happens is the color transition occurs over the course of 8.3 in pH units to 10.0. So if here is 7, 7 has no color. Here is 8 and 9, and then once you get to 10, it fully turns into that hot pink color. So it goes kind of a pale pink, and then a more bright pink, and then finally this hot pink. Another indicator, methyl orange, has a pH transition range from about a 3.1 to about a 4.4. So what that means is that you can kind of see here if this is 0 for red, 1 we have a red, at pH of 2 we have a red, and then all of a sudden once we start to get from a 3 to a 4 you can kind of see that it's this orangish color. And it's orange because it's transitioning from red to yellow. It's a little callback to your art days. If we mix red and yellow together, you get orange. So from about a pH of 3.1 to about 4.4, you get orange. And then anything higher than that, you have a yellow color. So we'll go back to our example again. If I would take something that has a pH of 3 and I would put methyl orange in it, it would actually be orange in its color. If I took my thing that's a pH of 9 and I would go back here, the pH of 9 or 10 would be a yellow color. Okay. There is another indicator called thymol blue. Now, thymol blue actually has 3 different colors that it transitions from. So it's not just flipping from one color to another, plus its transition color. It actually has several of them. I know this because if you look at the range here, we have a range of 1.2 to 2.8 and a range of 8.0 to 9.6. So what that tells me is I'm going to see 2 different color transitions. In my first color transition, if I have a pH of 0 or a pH of 1, I get a pink color. But then once I switch from about a pH of 1.2 to a pH of about 2.8 or almost 3, I get a color transition happening here, and I get orange. So if I would take a pH 2 solution and put a drop of thymol blue in it, it would actually be orange in its color. Then from a pH of about 3, kind of all the way to about a pH of just under 7, I get this yellow color. And then my second transition range starts, and then I get this kind of funky grayish, greenish blue color. And then from a pH of 8 to about almost a pH of 10, I get this weird transition, and then it turns blue. So if I would take my solution with a pH of 10 this time and I would put it into here, put the thymol blue in, it would be blue. Okay, hopefully this is kind of making sense. We'll go over 2 more. Brome thymol blue has a 2-color system, so it's yellow and blue. Green is its transition color, and I know it only has 2 different colors because it has a pH transition of 6.0 to 7.6. So what that means is that anything below a pH of 6 is yellow. Anything in that range from 6 to almost a pH of 8, it transitions into this greenish color, and then it flips to blue as it's higher. Okay? And then my last one is phenol red. Phenol red has a transition zone from a 6.4 to about an 8.0. So what that means is that if I have a yellow color, it indicates something that's got a pH of 6 or lower, or 6.4 or lower, and then it transitions to a reddish kind of dark pink color, and in here you get kind of a light pinky orangey stuff happening. So with your indicators, what happens is, again, they are sensitive to pH. So they transition from one color to another with a middle color. If I have something like thymol blue, which has 3 different colors to it, technically I have a starting color, a transition color, my middle color, another transition, and then my final color. And it all depends on pH. Your assignment is going to be to see if you kind of understand how this works. So what you're going to be given is a sheet, and then I'm going to show you the pH of some different liquids, and then you are going to have to see if you can predict what color they are. If you find yourself struggling or having any questions, remember that we have the meet sessions that happen every day from 10:30 to 11, and if you have any questions, we can answer them there. All right? Hopefully this is pretty clear, and if you have any questions, let me know.